So geometric series means we're summing a geometric sequence. Geometric sequences are things like A times R to the n minus 1 was the general form we came up with before. N is going from, usually we start at 1, but we could start at other numbers. And since I didn't say partial sums, when we usually say series in calculus, we mean infinite. So I'm going to go to infinity. Now, infinity is not a number, so that's kind of weird. So what this really means is the limit as n goes to infinity of the sum, put I in the sum, put n as the end of the sum. It means look at the sequence of partial sums and explore what they are doing. Now, I showed a trick on how these work a minute ago. That trick summarizes for things like this right here. You get the first term minus the last term bumped up by 1. So that's going to be A times R to the n, based on our previous example. And in the denominator, I'm going to have 1 minus R. So example of that was back here. Here's my first term. Here's my general term bumped up from n minus 1 to n. And then in the denominator, I have my 1 minus my R there. And what we want to know is, in general, what is the limit as n increases of things that look like this? The only place there's an n is this term right here. So this question, the answer to this question boils down to thinking back to a geometric sequence. What kinds of geometric sequences converge? So just looking at the limit as n increases of A times R to the n. N is my variable that's changing, A and R is fixed. So this boils down to what values of R lead to convergence. Well, the examples we've seen so far, we get convergence for R equals 1/2. We got convergence for R equals 2/3. R could be anything. R could be 2. If R is 2, then my sequence is something like 2, 4, 8, 16, 32. What's this sequence doing?
Diverging.
It's diverging. Yeah, this increases forever. Diverges. Anybody want to take a stab at what kinds of values for R diverge and what converge? If R is less than 1, now that's assuming R is positive, but could R be negative? Turns out it could be. So more generally, what we're going to find is we're going to get convergence if the absolute value of R is less than 1. That translates as R has to be some number between, oops, get rid of the equal sign there, 1 and -1. What if it was 1? What if R equaled 1? Put that down here. R equals 1. 1 to the first power is 1, 1 to the second power is 1, 1 to the third power is 1, 1 to the fourth power is 1. R equals 1, the sequence does what? Converges. It's stuck at 1. What if we add up a bunch of 1s forever? 1 plus 1 plus 1 plus 1. I never stop. It's infinity. It's going to keep getting bigger. What about R equals -1? What's that doing? As a sequence. Well, -1 to the 1 is -1. -1 squared is 1. -1 cubed.
1, -1.
-1. -1 to the fourth. What's this sequence doing? It's oscillating. It's not going to a fixed number. Therefore, it diverges or converges. It diverges because it's not going to a fixed number. Yeah, this is divergent. If we add stuff up, what's gonna happen is adding up ones, well, that grows forever. What if I add up -1, then 1, -1, then 1? What if I did the sum as I goes from 1 to infinity of -1 to the I? Well, the first sum, looking at the partial sums, would be -1. -1 plus 1 is 0. 0 plus -1 is -1. -1 plus 1 is 0. What are the sums doing when R is -1? They're oscillating also. Instead of oscillating between -1 and 1, it's oscillating between -1 and 0. Is that convergent or divergent?
Divergent.
Divergent, yeah. So it turns out for the sequence, we get convergence at 1 and divergence at -1. For the series, we get divergent for 1 and -1. But in between, it should always be convergent because we're always going to have a smaller fraction of what we started with, right? If R is between -1 and 1, it's a proper fraction of what we had before. So this formula right here, that will go to 0 if the absolute value of R is less than 1. If that's the case, then all I'm left with is the first term divided by 1 minus the common ratio for a geometric series. Kind of cool. So let's look at another example to test this out. Let's look at the sum as I goes from 1 to infinity, that we could call S, of 1/3 to the power n. Actually, let's make it -1/3 for fun. What's that going to look like? Well, the first term here would be -1/3. And then the second term would be +1/9. Then it would be a plus -27, -1/27. And it's going to keep going. So I want to figure out what this goes to. Now, theoretically, we just calculated that should go to the first term, which is, let's see, this needs to be, yeah, we'll leave it that way. The first term is -1/3, and the common ratio, it's got to be 1 minus the common ratio. So -1/3 in the bottom. That should be -1/3 divided by 1 plus 1/3, which is 4/3. The thirds divide out, so my claim is this should add up to a -1/4 in the limit. Will I ever get to -1/4? Answer is no, but we'll approach it. Let's give it a try in Desmos, see what happens. So I want the sum. N goes from 1. Let's go up to 10 to start with. Oops, wrong place. Here, please. Parentheses, 1/3, close parentheses, raised to the power. Oops, I missed the power apparently. No, I have the power. N. So after 10 terms, 0.49. About 100 terms. 0.5. Oh, do I have a mistake in my calculation?
You want a third negative?
Let's see, minus -1/3, so that should be plus 1/3. 3/3 plus 1/3 should be 4/3. Divide the thirds out should be -1/4. Okay, so let's see. I'm starting with 1. That should be that. So the first term is -1/3, and then we're multiplying by 1/3 repeatedly. Oh, we got the negative here. There we go. 0.25. Okay. Now Desmos said the 100th one is exactly 0.25, -0.25. Is it really? No, it just ran out of computing power. So that's the best Desmos' ability.